So the story I'm going to tell you is it's going to have similar conclusions to what Brian and Mike talked about, except that I'm going to tell it differently. So I'm going to come at it from the research point of view. So to start with, I guess most of you know about eBay, but I want to know how many of you know the answer to this question. This was the first item that was ever sold on eBay. So when you look at large amount of data, you want to know what was the first data point that was ever created. So Pierre Omidyar, who started the company back in 2005, Labor Day weekend, he was building up this auction site, and he was trying to look for something to sell on the site to see if it works or not. He used to have a cat. He used to play with this cat with a laser pointer. And he used to point the laser pointer at the wall. The cat would jump up and down, and that was kind of entertained the cat. Then it stopped working one day, and he tried to fix it. He changed the bulbs, he changed the batteries, etc. It didn't work at all. So he said, maybe this is something I could try and list on this site that I'm building called Auction Web. He put it up on the site, and he said, it doesn't work. I tried to fix it, doesn't work. But he listed it as a 99-cent auction and said, let's see how many people are interested in something like this that doesn't work. People started bidding on it and bidding on it. And anybody has a guess for how much it's sold for? If you don't look it up on the internet, I would appreciate an answer. Any guesses? $5. How come I always get $5 as an answer? Sold for $14.83. And it sold for $14.83. Then he contacted the buyer and he said, do you know what you're buying? And he said, it's broken and it can't be fixed. He said, yeah, I absolutely know what I'm buying because I'm a collector of broken laser pointers. And so, so just when he realized that one man's trash is another man's treasure. And that's really the seed of our data. And of course, for scientists like me and my team, this caused a huge set of problems. Pretty much anything that you could ever think of selling could be sold on eBay. And that's the kind of data that got created. Here's another example of that. I think people at the back can see. Anybody knows this story? We have a lot of marketing folks here. They can identify with this story. So this was a woman who listed a cheese sandwich. Actually, it was lying in a freezer for 10 years. And she listed it on the auction block at $9.99. And she said, well, I took it out after 10 years, and if you carefully look at it, you can see the face of Virgin Mary. And people started bidding on it, and guess how much it sold for? Any guesses? $28,000. And usually when I show this example in tech conferences, they say, oh, who was that idiot who bought it? It was bought by a marketing firm out of Las Vegas, and they got written up in Wall Street Journal and Business Week, et cetera. And they were interviewed at CNBC, and they said, we've never run such a successful $28,000 marketing campaign. So again, the point was that, the point is that eBay often sees these kinds of data and complicates the way we look at data, and we draw analysis out of data. But of course, this is not what typically pays our bills. What pays our bills is the kind of stuff that sells on the site. So here, just to give you an example of the volume of data that sells on the site, about every second, $1,400 worth of goods sell on the site. A vehicle sells every 2 minutes. A partner accessory sells every 3 seconds. A diamond jewelry sells about 83 seconds. And a Timberland shoe sells every 10 minutes. And a trading card sells every 6 seconds. So this is kind of the constant volume of stuff that we see on the site and that get transacted on the site. And of course, once in a while, you do see those weird items that show up and create a lot of buzz. So here's another way to slice the data. Now, on the site, you see about 10 to 20 million items listed on a daily basis. With mobile being a big new entry into this space, we see that playing a significant role. And as we track the mobile behavior on the site, it's a location, the time of day, the kind of transactions or the kind of behavior you see, we collect a ton of data. We see about 300 million queries a day, about 150 plus million items are live at any point of time, about 100 million plus million users are active at any time. 4 out of items are listed as one of a kind. So we saw some examples of one of a kind items. And this causes challenge. When I give out examples, you will see why I'm giving this out here. one-of-a-kind causes a lot of problems for people who want to analyze data, right? Because you're selling your iPhone, I'm selling my iPhone, but I want mine to look unique as compared to yours, or different as compared to yours. But for data scientists, we want to kind of match them up. So this causes huge problems. Over 30,000 categories of items, but at the same time, when we have all of these dimensions, most buyers hang out in one or two categories, and most sellers hang out in one or two categories. So you see this huge skew in the data. We have a lot of dimensions of the data, but very few data points are actually populated. And if you're doing data science, this is a huge problem. Most of the time, what you're looking at is sparse data, and standard techniques don't work here. So I'm going to talk a little bit about my research team, what we do. These are typical scientists, mostly PhDs, working in a variety of areas, machine learning and data mining. So this is what a computer science fields, what in industry we call data scientists. These people are, again, building algorithms, creating machines that are intelligent, that can understand data better. Right? Text mining and natural language processing, these are people who, again, try and build algorithms for understanding text and parsing text out of languages, parsing natural language entities out of text. Computer vision, people who understand images, voice, OCR, video, people who can analyze that kind of data. Economics, of course, people can look at data and do experiments or draw conclusions economic conclusions out of those. User behavior analysis, information retrieval, and info visualization. So these are the diverse set of people that work on my team. And here's another way to look at these people. And actually, before I go to that, here's a class of data that all of us look at. So pretty much all of the research that we do is data-driven. And the kind of data we look at is user data. So when I say DW, it's actually, and these come from different sources. Some of them are sitting in data warehouses. Some of them are actually sitting in machines that serve up search. Some of them are sitting in Hadoop clusters. Some of them are actually on websites and standard file systems. So it's all over the place. User behavior data, product or item data, query or search data, transaction data, feedback data. Feedback is one of the primary entities in eBay to measure trust. Image data, communication data, that is member-to-member email messages data, and any competitive or crawl data from the web, and general event, real-time event data, which is user behavior, click-through, clickstream data. So this is kind of all of the data that the scientists look at. And another way to paint a picture of our scientists in the team is that, they're all, this is like the story of the elephant and the six blind men. It's the same elephant. There's a distributed platform at the bottom. Everybody's looking at the same data. They look at it differently. They draw different conclusions, and their goals are very different. So if you look at an economist, you look at a human-computer interaction person, or if you look at a search or a machine learning person, they're all looking at the same data, but at the same time, the way they look at the data, the way they tear down the data, the way they ask questions is different because they're trained to look at data differently. And I'll give you some examples of that as we go on. And if you look at a corporation, actually you can take the same picture, and one of the things that we did about 6 years ago was we said, we need to democratize data. In the past, before any time an analytic report had to be run, we had to run to the analytics team and say, can you produce this report for us? And in research, actually Brian gave a great example of two engineers hacking up a Hadoop cluster. This exactly, I thought he just told my story. It happened in my team back in 2007 when two researchers hacked into NFS and created the Hadoop 15, even before Facebook actually published their Hadoop deployment. And they showed that reports that would take 8-9 hours to create could be created in 8 minutes just by parallel processing them in a very simple way. Not only that, we built tools on top of that to say, hey, people with different roles in the company, they all should be data-driven. If you're research, of course, you should be data-driven, but even engineers should understand, debug, or build features on the side and understand what those features do and extract the data, and we will understand the data as well. Product management, analytics, business, everybody has to be able to understand and look at the data. So one of the things that we did in the labs was, starting with that, build a set of tools that would open up data to all the different people and provide access to them in different ways. So let me say one thing about the data. This kind of slide is a little bit out of place. One thing we learned, especially as computer scientists, is we love to claim that our algorithms are better than other people's algorithms. We publish papers, we say mine is 10% better than yours. And one thing that we learned as we threw more and more data at the system was that first thing you do is try simple algorithms, because complex algorithms take longer time to debug, longer time to run. So if you throw more data at it, actually you can do much better than just devising more complex algorithms. So typically what we start when we do research is we kind of say, hey, we need some training data, and we build a model based upon the training data. And as we add more data, one or two things can happen. Either it'll converge with the model, or it'll kind of produce new kinds of information. When it provides new kinds of information, it probably proves to you that your model is simple, too simple, or incomplete, in which case you have to throw away your model and come up with a new model. And come up with a new theory. And this is kind of what you do as you throw more and more data at it. And the biggest part of this work is actually, when you get more data, how do you throw away data and keep the kind of data that is really useful for your system is kind of, that's the art of all of this. Okay? So typically in research, what we do is, because we get a continuous stream of data on a daily basis, we have created this framework where you have a data pipeline coming in, whether it's user behavior data, whether it's transaction data, and you produce result streams. But at the same time, tomorrow, if you run the same algorithms, it's looking at different data and creating new kinds of training data and producing new kinds of algorithms. So that's kind of how we've architected our systems. So this goes back to one of the the multi-layer architecture that we created for democratizing data within the company. So at the bottom, we have all of eBay data. Then on top of that, we have Hadoop cluster. But if you ask most people to go to Hadoop cluster, then they got to get trained. And you got business folks and product folks who are not really trained to program in Hadoop. So we built several APIs or several layers of interfaces over these clusters. So for example, for engineers, we have Java API. For people who can do SQL kind of stuff, we built a query language on top of it. For business guys, we said, well, you just want to do point and click, so we built a visualization layer. And then for a lot of people, they want to just plug into the rest of their code, so we provide plug-in layers on top of that as well. So we built this nice architecture. Now, depending upon where you come from, you can access the same data, but different kind of interfaces, whether it's a visualization interface, whether it's a programming interface, or whether it's a query interface. You can do all of that stuff. So, and what we also did was we looked for repeatable design patterns in data aggregating and data processing, and we abstracted them out and provided them as tools or elements for processing this data to these different teams. So I'm going to give you 4 examples. I don't know if I'm going to have time to do all the 4 examples. And these are widely different examples, and they're all looking at the same data, but at the same time done for different purposes. So the first one is related to search, is actually looking at user behavior data. The second one is an example from economics, which is more of economic experiment. And third one is from text mining, and last one is from computer vision. And you will see that by looking at data in interesting ways and careful ways and parsing the data carefully, we can actually get much more bang for the buck than just building new algorithms. So the first one is a search example. And all of these examples are live on site today or is being used by the production system. That's kind of the beauty of it. So when you go to any search engine, you have a, I don't know if there's a laser pointer works. Okay, so you have a search box over there which says Xbox 360, and quite often, most search engines provide you related searches at the bottom. Because if the user query is too specific or too generic, the search engines don't work very well. So you want to show related searches. So right below the search box, you see PS3, Wii, PlayStation 3, Xbox One, and so forth. And you'll see this in Google, you'll see this in YouTube, pretty much everywhere, the notion of related queries. And one of the things we want to do was to build a good algorithm that will keep the users on the site so that they don't either get frustrated with either not getting any results or getting too many results. So that's kind of the target of this project. So the approach we took was, one thing as I pointed out, very few users on the site know a lot about the site, and a lot of users are naive users who do not know how to search. So the approach we typically take in data mining or building algorithms is that take the intelligence that the advanced users have and build algorithms around it using that and apply it or provide it as an interface to the naive users. So for example, here we have 2 users. Look at the bottom example. One user comes in and says, helicopter volitation spare parts cheap. That's the first query he types into the site. He doesn't know, he doesn't get good results. Then he changes it to helicopter volatilization replace parts. He doesn't get good results. He types in another query, helicopter volatilization spare propeller. He doesn't get good results. He exits the site. And this is a typical example of a naive user. Another user, an experienced user, he comes in, types in helicopter volatilization spare parts cheap. He recovers a little bit and he types in just helicopter volatilization, and then he types in helicopter volatilization blades. He finds exactly what he wants. He views a few items and does a purchase. So what we want to do is take the intelligence of this user and provide it as an experience to that user. And that's kind of what the query suggestions does. So this requires us to mine data over many, many days, many, many months of all the users and provide, build an algorithm on top of that. So first step in all of this is cleaning data. If you just look at raw data, this raw data is littered with bots because many of the crawlers come to the site, they do searches, and they completely bias your algorithms. So for example, here's an example. If you don't clean your data, what happens? So there's a query named query calculator, and if you do not dedupe user association data, if you do not clean your data, then you'll get related queries as fluke, Texas Instrument adding machine, pocket knife, TI-84 scientific calculator. They're kind of sort of related, but not exactly. Once you clean out the data, once you dedupe the users, once you remove the robots, then actually you get much better related suggestions, which is Casio calculator, scientific calculator, HP calculator, Texas Instrument, TI-84 adding machine. So one big part of this work is cleaning the data. Clean the data, meaning understand the data better, throw away duplicates, throw away garbage, and you'll get much better results. You don't even have to build new algorithms for that. So another thing, I don't want to go to the details of this chart, but one thing you do find with query suggestions is that most of the time users react to good suggestions when they cannot find good results. But at the same time, you don't have many examples of cases where you do not have good results. So what that means, for example, if you look at the first graph over there, you will see that about 80% of the queries are covered by 10%, 80% of the sessions are covered by 10% of the queries. And for the remaining queries, you have very few examples. But on the other hand, if you look at the last slide on the right, is query suggestions are used by users when they have very few results. So most users want help when they're in a sparse space, but at the same time, we don't have enough data when users are in a sparse space. So what do you do in that case? You basically have to look at more data. So here's a very simple chart of how we did the live experiments. So there are two bumps you see. This shows x-axis is the time axis over a period of time when we were doing query suggestions and how we got the user click-through rate to go up. So the first boost we got when we just cleaned the data. When we cleaned the data, removed the robots, and looked at good quality data. And then the second big boost we got by just looking at more periods of data. So when you have these sparse queries that don't occur very often, you have to go back in time, go back 6 months, go back 9 months, go back. So we started with 3 months of data. We actually went up to 3 years of data. And that's the amount of data we had to look at to provide better suggestions. So again, given this platform, the Hadoop platform we had, and the way to do an extensive analysis of user behavior, we could look at large amount of data. And think about it, we are talking about 300 million queries a day. So now go back 6 years. That's a lot of data to look at. And we could do that in pretty much near real time. Okay? Now, the second example is going to be widely different. So this is, if there are any economists in the room, you might identify with this. So most economists look at, try and understand markets like sales strategies or prices, et cetera. And what do? They run simple experiments. Either they do experiments in the labs or they run some kind of field experiments. A simple kind of field experiment quite often economics papers, economists do on eBay is, an economist would go and buy 100 Pokemon cards, sell 50 one way, sell 50 another way, and collect all the results and draw conclusions saying, oh, consumers are violated this way or consumers benefit that way and so on and so forth. And we were looking at these volumes of data that we have, and we have over 100 million users, and we said, well, if you have 100 million users, many of them are power users, and if you are a seller and you had 100 Pokemon cards to sell, what would you do? You would be probably changing your prices often. You would be probably changing your little features often. So any economic question that we had, we found out that our sellers were actually acting like economists, and they were constantly running experiments. So if I'm selling my Pokemon cards, should I offer free shipping or should I charge for shipping? Or should I put 2 pictures in or 4 pictures in? And these were questions sellers often have. And for any economic question that we had, we found hundreds of thousands of experiments actually running on the site as we were looking at it. We didn't have to actually run the experiments. Our sellers were actually acting like mini economists, and we just needed to analyze the data at scale and understand this. So here's a simple example. There's a policy question. Should gallery images be free? So eBay allows sellers to post images. Now, should eBay charge for images or not? Now, the question is, you want to say, do more gallery pictures make the item more sellable or the products more sellable? So if I'm selling the same product with 2 images, 2 pictures versus 5 pictures, I mean, economists would say more pictures means more information, so it should be generally good. But are there experiments of this kind running on the site? Are sellers who have multiple items of the same nature selling on the site creating these experiments, or do these experiments exist? And we found hundreds of thousands of experiments on a daily basis running on the site. So we just needed to analyze it. We didn't have to actually do any kind of A/B test. Our sellers were doing the work for us. So we created this notion of experiment where it's a seller item title leaf category as a key or an experiment ID, and then we created this platform. We kind of married the economist with the software engineer and created this whole platform, and what I used to call an economist in a box, which is you ask this Oracle your economic question that translates to an API, and it comes back with hundreds of thousands of examples of economic experiments. Now you can take those experiments and run your favorite stata or statistics on it and come up with your economic conclusions. So I'm going to show, and this we built it as a software stack using user data. And I'm going to show you an example of one of these tests. So what is the effect of adding pictures to an item? eBay charges for extra pictures. Do they help? So basically, we want to look at all of this data. And we found that for the same item, as you see more and more pictures, the probability of conversion goes up. So up to about 8 or 9 pictures. Or another way to look at it is, does the sale price go up? So for the same item, when the seller puts in more pictures, you do see that the sale prices go up about up to 5 pictures. So you can say that if you're a seller, you want to encourage the sellers to put more pictures for the products, which means they will convert better and they will be willing to pay a listing fee, a picture fee. Alternatively, you can say that, well, they're converting better, which means eBay makes money out of it, so you don't charge for it. So now you can kind of draw the separation of how much money we make out of these sellers and create a policy. But the point of here is that just looking at data, we could answer these questions, which would otherwise take weeks or months of A/B tests or A/B experiments or field experiments, and we could avoid that pretty easily. Okay. And there are several other questions that can be answered with this. For example, should I sell products by auctions or fixed price? What should be the starting price of an auction? Should I offer free shipping or not? What day of the week should I list these products in? Is a top-rated seller better than a non-top-rated seller? And so on and so forth. All these questions, or what are the charity effects of an auction? Meaning, if you list an item and say, I'm going to donate 20% of my product to charity, do people pay more for it or not? And economists constantly have these kinds of questions. We don't really need to run any field experiment. Field experiments are constantly running. We just need to pull the data and analyze it. So this was the example number 2. So the third example is going to be related to text mining. I'm just going to show a couple of charts. And as I said, we saw the example of the Virgin Mary cheese sandwich or the broken laser pointer. One of the challenges we have in eBay is about 80% of our items are one of a kind, which means people kind of can put whatever they want to put in the description, and they're not cataloged, which makes it extremely hard for us to create a search experience because our search experience is just keyword-based. So one of the big projects was to mine the item descriptions to extract metadata out of these items. And what we did was, again, for example, here's an example. So there's a Barbie doll, and this is kind of the description that you see. Here's a Barbie 1999 premiere night, home shopping special edition, blah, blah, blah. Never removed from box, doll in mint condition. Remember, it's a beauty, it's 11 years old, and so on and so forth. And the kind of information you want to get out of this is, year is 1999, model is premiere night, edition is home shopping special, hair is blonde, gown is purple and silver, and so on, and condition is new. So we built a platform where, again, this is a Hadoop platform where items come in. We have these description mining algorithms that run and produce this metadata. And as new items come in, the metadata gets constantly updated. So this is done at a large scale, about 15 million items a day on a continuous basis. So this is done as a platform. So I won't have time for this computer vision example. But again, this is kind of where the world is going. So with the mobile devices, we are seeing a ton of commerce experiences built by not typing in, but at the same time speaking, or by taking pictures or taking video. So we said, well, computer vision algorithms are hard, so let's take a data-driven approach to doing this. And if you look at typical computer vision space, the largest data set computer vision people have or researchers have is 20 million examples. But today with Pinterest and Flickr and all these things, you've got a ton more data. Even in eBay, you've got about 100 million images we collect a month. So can we build a data-driven approach to recognizing pictures, meaning identifying picture quality, recognizing objects in the pictures, recognizing the colors and textures of the dresses that might be selling? And we took a completely data-driven approach. I'm going to skip over this, but it shows you how we use Hadoop and MapReduce combined with a GPU kind of an architecture where one of the things with computer vision algorithms is they tend to be compute intensive. So you split the data and you do a lot of the computation in the local node, which a local node are GPU nodes, which means they have highly parallel in-memory processors which can be run to do the strong computation. But at the same time, the data intensive part can be done over Hadoop. So we built this thing, and we launched the eBay mobile fashion app last December, and actually the UK version launched this year, and it's really based upon this algorithm that we built in the labs. And we could look at millions of images coming in, build algorithms that were simple algorithms, but at the same time solve the problems of identifying dresses, identifying colors and textures and styles of dresses, and help the users buy based upon picture. So I'm going to skip to the last slide here. Basically, I just want to share a few thoughts. Nothing very different from what the previous speaker said, but at the same time, important. So Peter Drucker said, you can't manage what you can't measure. Actually, you can't measure what you can't manage. So you have to be able to get handle on this large amount of data that you have, and you have to build tools around them, and you have to have the right kind of platforms for them. Okay, and in our context at least, and probably applies to you as well, our data comes from a variety of sources, so you have to have systems that manage this variety of data sources, and you have to do science in a data-driven way. You have to understand data well, and all scientists have to be data-driven. That's more important, and that's kind of what I preach to the scientists in my team as well. Okay? And we need data people across the organization, so whether you're an engineer or a product manager or an analytics person or a researcher, you have to be a data-driven person. And that's becoming more and more important within a company. So if you're relying on the analytics team to produce the reports for you or to give you insights in the data, you're not going to be able to scale very much. Okay? Thank you.
Thank you very much.